Hey there, chemists. Welcome to another exciting lesson in our nuclear chemistry unit. Today we're going to be focusing on nuclear reactions, specifically fission and fusion reactions. And I wanted to start today's lesson off with just this quick quote. President Joe Biden has set ambitious goals for fighting climate change, to cut U.S. carbon emissions in half by 2030 and to have a net zero carbon economy by 2050. The plan requires electricity generation, the easiest economic sector to green, analysts say, to be carbon-free by 2035. So where is all that clean electricity going to come from? So let's talk a little bit about the electricity usage from the U.S. And I tried to find a more up-to-date pie graph, but I've come to find that they only release them every 3 years or so. So here's a pie graph of our energy consumption during 2019 in the United States. So note that 37%, the largest amount of our energy, comes from petroleum, 32% from natural gases, 11% from coal, 11% from renewable energy, and 8% from nuclear electric power. So approximately how much of our current, or in 2019, energy was carbon based, okay? How much of it was carbon based? So taking a look here at the at our pie graph, you have to ask yourself which of these are carbon based. So petroleum here is in fact carbon based. Okay, our natural gas portion of the graph over here is carbon based, and the coal over here in the gray is also carbon based. And so if we were to calculate how much of it is carbon-based, 37% plus 32% plus 11% is going to give us about 80%, of our energy is currently carbon-based. And so that what is interesting to me about this quote is that it's telling us that by 2035, we really need to be making an effort to be have no carbon really being used for our energy sources. And so notice that there's two other kind of energy sources that we use frequently: nuclear power plants, which we're going to be talking about, as well as renewable energy. So I just wanted to kind of run through some of the options of renewable energy that we may or may not be using. Now, when we think about renewable energy, a lot of us tend to think of right off the bat maybe wind energy, right? We've probably seen those turbines before, okay? Or maybe hydro energy, using water to kind of help us generate power. We have geothermal energy, which is using the heat from the earth. And then lastly, the big and probably most common is solar energy, which I wanted to talk about for just a couple of moments. So solar energy is used frequently, and you know, I see it more frequently maybe in the like the suburb areas or Long Island. But what I thought is really cool is that in California, they actually introduced a new bill and new standards for building homes. And so in the latest round of standards, which took effect in 2020, there is a major advancement for clean energy. Besides the requirement that all new homes under 3 stories install solar panels, a first for the nation, they also help incentivize energy storage and include a host of energy efficient upgrades that will collectively slash energy use in new homes by more than 50%. So California has made this law, the first in the US, to kind of incentivize people to be using solar energy, and any new homes built up moving forward have to include solar panels. So where do solar panels pull their energy from? Well, solar, right, comes from sun, right, the sun, okay? And so we have here our solar panels pulling energy from the sun. Now, the question is, where does the sun get that energy from? And the sun gets the energy from nuclear reactions, specifically nuclear fusion. Okay, so let's go ahead and talk a little bit about nuclear fusion. Okay, so nuclear fusion, okay, is going to be the process that takes two light nuclei, okay, and it's going to form one heavier nuclei. Okay, and it produces energy. Now, fusion, the way that I like to remember this, if you've ever heard of the term fusion before, it's really talking about bringing two things together. Maybe you've heard about fusion in terms of like fusion cuisine, which takes two different types of cuisine and brings them together. So the way that I like to remember the difference between fission and fusion is fusion literally brings things together. So let's take a look at some example of what's going on here. So our sun combines hydrogen to make helium. So two hydrogen nuclei come together to form a heavier hydrogen nuclei and a positron. Then that heavier hydrogen nuclei combines with another hydrogen nuclei to form 3,2 helium. And then we get two of those 3,2 heliums to produce 4,2 helium and two more hydrogen nuclei. So it's a self-sustaining reaction that continues on. So it essentially continues to use these hydrogen, but then spit them back out. It makes energy, and that's where we get our energy from. Now, did you know that not only is our sun undergoing fusion, or our fusion reactions happening at the sun, but also at a lot of the other stars in our universe to help us produce the elements we find on Earth. So let's take a look at a couple more examples here. So we have 12,6 carbon and 12,6 carbon. It's going to give off energy and a proton, okay? Now, so what is our missing component here? Well, our mass numbers are 12 and 12, giving us 24, but we do have a proton here. So that means that we have 23, and then we have 6 and 6, which is 12. But again, we have a proton, which is using up the 1, and therefore this is 11. Element number 11 is sodium. So this is sodium. And then down below, we have here the sulfur being created by 16 and blank becomes 32 and 1. So this is going to be 17. And then, of course, we have 8 and 16. This is a 0, so this is still 8, making this 7, 8, or 17, 8 oxygen. So a slightly heavier isotope of oxygen. All right. Now, what quantities are conserved during all chemical reactions? And this is going to be really important because nuclear reactions seemingly break this, and we'll talk about why that is in just a moment. But in all chemical reactions, mass, charge, and energy are conserved. So all three, mass, charge, and energy. So taking a look at this graph here, and I left work with your neighbor, we're going to all work together. Let's take a look at the graph to the left. What appears to happen during this reaction? So notice how as the reaction proceeds, we have our energy being released as we expect to be seen, but note that it appears that the mass is decreasing, okay? So it appears that the mass is decreasing. Okay, and that is actually not true. The mass is not, well, it is actually kind of true that the mass does appear to decrease. And from up above, we were saying mass, charge, and energy have to be conserved. And so what's happening to that? Now, in both fission and fusion reactions, the mass of the product is slightly less than the mass of the reactants. And we wanted to know where that mass was going. And so the extra mass, or what we call the mass deficit, is converted to energy. And some of you may or may not be familiar with the equation. E equals mc squared. Energy is equal to mass times the speed of light squared, okay? And so when we are talking about this mass deficit or this mass conversion, 1 gram creates 9 times 10 to the 13 joules of energy. So fusion reactions, seemingly really great, right? We know it's happening at the sun. We know it's taking hydrogen, which is plentiful, and it's using that hydrogen to create energy, and then it's creating more hydrogen in the process, so it's self-sustaining. So they've been proposed as an alternate power source, but why are they not viable on Earth? Why can I not have a fusion reaction on Earth? And we have to really think about the sun and kind of what is going on at the sun, right? The conditions just on Earth are not feasible for the fusion reactions. Now, first and foremost, our sun is extremely hot, right? So there's conditions aren't correct. Okay, there's not enough activation energy or heat to start the reaction. Okay, and so when we talk about nuclear reactions occurring here on Earth, we're not talking about fusion reactions. Fusion reactions take light nuclei, really not dangerous reactants at all, and it's self-sustaining, but we just can't do it here. And so we instead use fission reactions. So nuclear reactions are used for an alternate power source. Nuclear power plants utilize fission reactions. So how is fission different than fusion? Well, fission, if you think about what that term really means, when something is undergoing fission, it's splitting. And so nuclear fission is when we have heavy, unstable nuclei that split into 2 or more small nuclei. And again, it still produces a lot of energy, right? Or else we wouldn't be using it. But when we talk about 11% of or 8% of our energy coming from nuclear energy, we are talking about nuclear fission. Okay. So let's take a look at what that looks like. We have here, I have an image of a nuclear fission reaction. Okay, and so in order for a nuclear fission reaction to occur or to start, what has to happen? Well, taking a look over here at our diagram, notice that we have our uranium-235, our unstable isotope. And in order to jumpstart this reaction, we are bombarding it or hitting it with this neutron. And that neutron is absorbed by the uranium-235 to cause it to split into 2 lighter elements along with another neutron. And then take a look at it continues forward like a chain reaction. So what has to happen? A neutron is absorbed by a heavy, unstable isotope. Okay? And so how would this maybe be represented in a chemical reaction? So taking a look at our reaction below, we have here our reaction, so uranium-235-92 with a neutron, and it creates a heavier unstable isotope, which produces 2 lighter isotopes with more neutrons and energy. So how do we know it's fission by looking at this? 1, we are starting with a neutron being absorbed, okay, but 2, we have heavier becoming lighter isotopes. Okay, now why does uranium-236 decay, right? We see that seemingly after it absorbs this neutron, it almost undergoes this natural transmutation where it just starts to decay. And we have to think back to our proton to neutron ratio. The more neutrons there are, the more unstable our atom is. So it's unstable because of proton and neutron ratio. So you might be asking yourself, okay, well, that's great. Fission's being used. So why do we use these nuclear power plants, right? What's the purpose of this nuclear power plant? Like, why can't we just use more renewable energy? Or rather, what's the draw of these nuclear power plants? And nuclear power plants are used for alternate sources of energy because nuclear reactions produce the most energy of any chemical reaction. Okay, so nuclear reactions are like no other reaction. However, and you guys, I've included this picture of Homer Simpson. If you've ever watched The Simpsons, he works at a nuclear power plant. But why, why are we not using them more then? If they give us the most energy, why do they only make up 8% of our energy? Because they're extremely, extremely dangerous. So on March 11th, this is the most recent one, but there are plenty of them, plenty of nuclear power plant disasters that you can look up. But on March 11th in 2011, the Great East Japan, I can't speak today, earthquake and tsunami sparked a humanitarian disaster in northeastern Japan and initiated a severe nuclear accident at the Fukushima nuclear power plant. 3 of the 6 reactors of the plant sustained severe core damage and released hydrogen and radioactive materials. And so you may or may not also be familiar with Chernobyl, which was the nuclear power plant disaster before this. But what ends up happening is when this nuclear radioactive material is released, right, it is going to start to mutate things we find in nature. It makes kind of that Earth area uninhabitable. And so what are some of the things that we could see? I have here a turtle with 2 heads. That's one strawberry with like 1 million different strawberries on it, a tomato with 1 million tomatoes on it, and a sunflower where each petal is now a different sunflower. And while they look really cool, right, they can be really dangerous. And additionally, why else are these nuclear power plants problematic? Because if you think about what we've learned now with half-life, things that are radioactive, things that undergo kind of decay, how long does it take to completely decay? The fact of the matter is that half-life is exponential, right? It takes a very, very, very long time for all of that to decay. And so millions of years would go by without all of this nuclear stuff decaying. So I want you guys to think about this, and it's going to be your entry question into tomorrow's class. But why do you think then it would be beneficial to produce energy through nuclear fusion rather than fission if we can find a way to do that? All right, everybody. Thanks for listening, and I'll see you guys tomorrow.